Chapter 18, Nuclear Chemistry. Here we have a picture of the sun. And the sun is doing nuclear fusion. It's taking hydrogen gas and it's fusing it into helium. And in so doing, releasing a massive amount of energy, which is why the sun is the energy source for all of Earth. And in this chapter, we're going to cover radiation, radioactivity, the types of radiation, alpha radiation, beta radiation, gamma radiation, radioactive disintegration series, measurements of radiation, nuclear energy, and the mass energy relationships in nuclear physics, and also the biological effects of radiation. Radioactivity is a spontaneous emission of particles and or energy from an unstable nucleus of an atom as that atom is radioactively decaying. Nucleons are protons and neutrons in the nucleus of an atom. A nuclide is a specific isotope of an atom. For carbon, you have carbon-12, carbon-13, carbon-14. For the radioactive nuclides, these are the unstable ones that are slowly breaking down. And they emit things such as radon and helium. And we're going to see which radioactive elements produce those later. Stable nuclides are not radioactive. They stay the same. They are not in a slow degradative process. The atomic number is the number of protons in an atom. The periodic table is organized by atomic number because that's the only subatomic particle that stays consistent. The same element can have a different number of neutrons based on the isotope. For example, carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. Also, elements can have different number of electrons based on their electrical charge, but proton stays the same. And so elements are recognized by their atomic number. The mass number is the number of protons plus neutrons. In our basic symbol, you have your chemical symbol of the element. The mass number is in the upper left, which is protons plus neutrons. Atomic number, just protons, is on the lower left. Uranium-238, therefore, has 92 protons because we see 92 in the lower left. Protons plus neutrons is 238. To find just neutrons, we take the protons plus the neutrons minus the protons, so the mass number minus the atomic number. 238 minus 92 gives us 146. Lead-210. To find the number of neutrons, we take the protons and neutrons, which is 210, minus 82 protons to get 128 neutrons. So how many protons, neutrons, and nucleons are found in the following nuclide? And here we have bismuth-210. Now we look at the lower left. Atomic number is 83, so we know we have 83 protons. So we know that A is already correct. But nucleons, or the protons plus neutrons, is 210, which should be the upper left, which again is correct. And then to find the neutrons, we would take 210 minus 83 to get the correct number of neutrons. So we take out our calculators, and we take 210 minus 83, and we get 127 neutrons, which is exactly what they have. Here we see different symbols. A neutron has no charge and a mass number of 1. A proton has a charge of +1, Z is +1, and a mass number of 1. Beta particle. A beta particle forms when a neutron decays. So a neutron can break apart into a proton plus an electron. And when these electrons are flying out of the nucleus, we call them a beta particle. And that is beta negative radiation that produces that. Positrons come from beta positive radiation. A proton decomposes into a neutron plus a positron, which is the antimatter particle of an electron. It is exactly the same as an electron, except it has a positive charge. So we see a positive charge just like a proton, but no mass. Because remember, electrons were 1,837 times lighter than protons and neutrons, so they get pretty much no atomic mass number. An alpha particle, this is a helium nucleus. You have 2 protons and 2 neutrons bound together. So, alpha radiation emits alpha particles, which are helium nuclei. Once they're emitted, they rip 2 electrons out of something, and that is how helium forms, which is why you find helium in the ground. Geologists find deposits of it in the ground because it forms from radioactive decay. A deuterion is a very heavy hydrogen nucleus. It's hydrogen, but it's an isotope. There is 1 proton and 1 neutron in the nucleus, whereas normal hydrogen only has a proton and nothing else in the nucleus. Radioactive decay is the continuous disintegration of radioactive nuclides. And this is independent of temperature, pressure, or chemical physical state. It has a half-life. A half-life is how much time does it take for 50% of what is there to disintegrate. And after 1 half-life, you have half as much as you started before. And then after another half-life, you have half again. So then after 2 half-lives, you only have 1/4 of your beginning materials. Here we see some different half-lives. Radon-235 has a half-life of 117 or 11.7 days. Radon-224 has a half-life of 3.64 days. Radon-225, 14.8 days. Radon-226, 1,620 years. Radon-228, 6.7 years. Carbon-14, 5,730 years. Carbon-15, 2.4 seconds, which is extremely rare. Uranium-235, 7.1 times 10 to the 8th years. Uranium-238, 4.5 times 10 to the 9th years. And so different radioactive elements have different half-lives. They can range from 1/10,000th of a second to billions of years. In general, you only get about 10 half-lives when you're trying to radiodate something. After that, you don't have enough of the original material left to accurately get an accurate date on it. And so that's why we use carbon-14 to date things. Like carbon-15 wouldn't be useful because 2.4 seconds times 10 is 24 seconds. So after 24 seconds, there is so little material left you couldn't get a date on it. And so carbon-15 is not useful at all, which is why you always hear about carbon-14. Because that gives you about 10 half-lives is about 57,000 years. And so you can date things pretty accurately up to about 57,000 years ago using carbon-14. That makes it much more useful for us. The half-life of iodine-131 is 8 days. So how much of a 32-gram sample remains after 5 half-lives? Well, after 1 half-life, you've used up half of it. So if I started with 32 grams, after 1 half-life, I only have 16 grams left. And then, after another half-life, I use up half of what I had left. Half of the 16, I have 8 grams left. After another half-life, I use up half of what I had. I have 4 grams left. After another half-life, I use up half of what I had. I have 2 grams left. After a 5th half-life, I have 1 gram left. If I had a 6th one, I would have half a gram. A 7th of a 1, 1/4 of a gram. An 8th half-life, 1/8 of a gram. A 9th half-life, 1/16 of a gram. And a 10th half-life, 1/32 of a gram. And again, at that point, you have so little, it's not a useful way to measure something anymore. So you get about 10 half-lives when we measure things by radioactivity. The relative amount of radioactive carbon-14 is stable in living organisms. Why? Carbon-14 forms in the higher parts of the atmosphere. And so extremely energetic radiation from the sun strikes Earth, and when it does so, it hits the nitrogen-14, and it has a nuclear reaction, and nitrogen-14 is converted into carbon-14. And then that carbon-14 slowly falls to the ground, where it is incorporated into living things. And living things have to eat. So every day you eat carbon from your food. And therefore every day an animal is alive, you get more carbon-14 coming into your body. However, when an organism dies, one of the first things they stop doing is they stop eating. And when they stop eating, what you then have is there's no more carbon-14 coming in, which means what's there just starts slowly decaying. So how many half-lives must elapse so that only 1% of carbon-14 remains? Well, after 6 half-lives, you have 1.56% of what you started with. After 7 half-lives, you have 0.781% of what you started with. So if the half-life is 5,730 years, how many years is 7 half-lives? Well, 7 times 5,730 gives us 40,110 years. So after 40,110 years, you have less than 1% of the radioactive carbon-14 in a biological organism as when it died. A 4-gram sample of radon-226 decays to 1 gram. If the half-life is 1,620 years, how much time elapsed? Well, this is, how many half-lives is this? After 1 half-life, 4 grams would break down into 2 grams. Then after another half-life, you'd only have 1 gram. So we have 2 half-lives, and 2 times 1,620 is 3,240. The half-life of gold-198 is 2.7 days. What mass of gold-198 will remain if a 12-gram sample decays for 13.5 days? Well, let's start with our 12 grams. And our half-life is 2.7 days. It goes for 13.5 days. 13.5 divided by 2.7 is 5. This is 5 half-lives. So the amount is cut in half 5 times. So after 1 half-life we have 6 grams. After 2 half-lives we'd have 3. After 3 half-lives we'd be at 1.5. After another we'd be at 0.75. And then after the 5th one we're at 0.375 grams. So every half-life you lose 1/2 of the remaining radioactivity. So notice at each half-life you're losing less because you're starting with less. Radioactivity results from an unstable ratio of protons to neutrons in the nucleus. Elements 1 through 20 are stable with a neutron-proton ratio of 1 to 1. But elements 21 to 83, the neutron-proton ratio gradually increases until bismuth has a ratio of about 1.5 to 1. If the neutron-proton ratio is too high or too low, the nucleus starts emitting particles to achieve a more stable nucleus. So basically, there's a stability with an equal proton-neutron ratio. Bismuth is our largest stable nuclide. Everything bigger than 83 is radioactive. And so here we see alpha and beta particles are deflected in opposite directions. Because an alpha particle was positively charged. It was the nucleus of a helium atom. 2 protons, 2 neutrons. A beta particle was an electron. And so the alpha particle, since it's positive, is deflected away from the positive. And the beta particle, since it's negative, is attracted to the positive. And so because they have opposite charges, they are deflected in opposite ways. The gamma particle is not deflected at all, because gamma radiation is just super energetic light. It is a photon of high energy electromagnetic radiation. So gamma rays are unaffected by the magnetic field. And we go alpha, beta, gamma because that's the Greek alphabet. Alpha, beta, gamma, delta, epsilon. And that is why science went down alpha, beta, gamma. Alpha particles are composed of 2 protons and 2 neutrons. They have a mass of 4 atomic mass units. 1 for each proton, 1 for each neutron. And a +2 charge. Because again, protons have a +1 charge and we have 2 protons. So it has a +2 charge. And that gives us a symbol for helium. So when you emit an alpha particle, you're emitting a helium nucleus, which is why helium is a byproduct of radioactive decay. Any radioactive nuclide undergoing alpha radiation is emitting helium nuclide. So uranium-238 breaks apart into thorium-234 and an alpha particle. Then the alpha particle will grab 2 electrons and become helium. Balance mass. The sum of the mass numbers of the products must equal the mass numbers of the reactants. You cannot gain or lose mass in this. And so if you're emitting an alpha particle, that means 2 protons and 2 neutrons are being expelled from the nucleus, but they still exist. In beta negative radiation, a neutron decays into a proton and an electron, but you still keep the 1 atomic mass unit. In beta positive radiation, the proton decomposes into a neutron and a positron, but still, both sides are 1 atomic mass unit. And you have to balance charges. So both sides have to have the same mass, both sides have to have the same charge, which is what we saw earlier. Then that's why in beta negative or beta positive, if a proton decays, you get a neutron and a positron. Both sides are +1, both sides have an atomic mass unit of 1. Beta negative radiation, a neutron decays into a proton and an electron. On both sides, the net charge is 0. Both sides, net atomic mass unit is 1. The mass has to be the same on both sides of the arrow. Charge has to be the same on both sides of the arrow. Bismuth 210 decays by alpha decay to form what nuclide? Well, 210 minus 4 is 206. And that will give us this thallium isotope. Beta particles. They are identical in mass and charge to an electron, because they basically are an electron. They're just coming out of the nucleus, which is why they're called beta particles. And here we see beta decay of Th238 can be written in 2 ways. But this beta particle is basically an electron, but that electron is coming out of the nucleus. It's flying out of the nucleus as a neutron decays into a proton plus an electron. So notice our product here has 1 more proton. Went from 90 protons to 91 protons because one of the neutrons decayed into a proton and an electron. Carbon-14 is a beta emitter. What nuclide is formed in the beta decay process? Well, if we emit a beta particle, that means a neutron had to form a proton plus an electron. So what we get is nitrogen-14, because that would be 7 protons. Notice the mass number stays the same. Carbon-14 is 14, nitrogen-14 is 14. The difference is carbon-14 is 6 protons, 8 neutrons. And nitrogen-14 is 7 protons, 7 neutrons, because one of the neutrons decayed and formed a proton and an electron. The proton stayed in the nucleus, the electron decayed. And so this is the opposite of how carbon-14 was formed. Gamma rays are photons of energy that are much, much higher in energy than X-rays. Loss of a gamma ray results in no change in mass or atomic number of a nuclide. And so the mass number stays the same, the atomic number stays the same, you're just emitting high energy photons of light, which is a gamma ray. Polonium-210 is both an alpha and a gamma emitter. So what nuclide forms in this decay? And that's going to be lead-206. Because we had 210 and then we release our alpha particle and we release our gamma ray, and that leaves us with 206 out of 210 because 4 are in the alpha particle. And it'd make more sense if you put a helium there. Penetrating powers of radiation. Gamma rays penetrate through a thin sheet of paper easily. So do beta particles. Alpha particles are stopped. So a thin sheet of paper is enough to protect someone from alpha radiation. Thin sheet of aluminum. Now we can protect against alpha and beta particles, but the gamma rays get through. And then a 5 centimeter lead block. That's like 2.5 inches of solid lead. Again, a little bit of gamma rays are still getting through. So gamma rays have a huge amount of penetrating power, and it's hard to actually shield something from that because they can go through inches of solid lead.